in the exact same pie. We'll probably have butter, or we'll have margarine, or something else. Not all of them at once. So we're going to use a Bayesian approach so that we can encode this prior information. So the x's are observed. We can put just a normal prior on our on the nutritional information for each ingredient. And we can put a normal prior on our errors. But in order to get this sparsity and this diversity, we're going to need to be a little bit careful with our prior on how much of each ingredient goes in each pie. So we're going to use, to get diversity, something called a spike and slab prior. So here we've got a plot that kind of shows what goes on with the spike and slab prior. Either you get a spike, which means you get a 0. That gives us the sparsity. That ingredient isn't included at all. Or you get the slab, which is the normal distribution here, which means that we sample from a normal to determine how much of that ingredient goes in it. So in like a traditional spike and slab prior, there's no dependence between which are zeros and which aren't zeros, so where the sparsity is. And this traditional won't get us the diversity we'd like. Instead, we're going to have to kind of tweak the spike and slab prior using something called a determinantal point process to get diversity. And so this is where we bring in the idea of like margarine versus butter and butter versus sugar, is that margarine and butter are quite similar if we were to plot them just in 2 dimensions that look like that, whereas butter and sugar are different. We could plot it like that. So one way to measure the diversity would be just to look at the areas of the induced parallelograms, and we'd see that we have a much larger area associated with diverse subsets of ingredients. So this is kind of what's going on in the determinantal point process. Instead of independently choosing these z's, which are indicators of whether or not each ingredient is included, we choose subsets proportional to the square of those volumes, which is the same as this determinant. So this motivates the determinantal spike and slab prior that we've defined for this factor model. And I'll pass it off to Marwan to I'll wrap it.
Thanks, Neil. So how do we go about actually incorporating the determinantal point process as a prior into the model? So here's the graphical model representation, and this is the standard latent factor model, the lambda, x, and eta. And the x's are observed, lambda, and etas are the latent variables. But we add the interaction between the etas and lambdas through this sort of process. So what happens here is that lambda becomes a kernel similarity matrix for the determinantal process, and then we sample binary vectors, z's, which sort of gate the etas. So what happens is that if z is present in the subset that we sample, we select a slab. So we select this component in eta. Otherwise, if z is 0, basically eta has to be 0. It comes from the slab component of the distribution. So mathematically, this looks like that expression, and every term in this product corresponds to the component of the graphical representation. So we have this probability distribution that comes from the determinantal point process, and we have this spike and slab delta function and the Gaussian distribution. Also, we have the standard normal error and the prior. So how do we go about inference in this model? Well, we can just do sampling and infer etas and lambdas through sampling. But it turned out to be very hard, so the sampling doesn't mix well. So we decided to integrate out the spike and slab distribution. So once we do that, we get this form where we have some function of x and z. And it turns out to be a convolution of 2 Gaussians in the lower dimensional space. So now we have these factors, lambda, and z's that are also latent variables. So we are interested in lambdas, but we're not interested in z's, so we just integrate them out, and we can do that within the standard expectation maximization framework. So what we do a stochastic EM that I'll talk about in a second to infer the latent factors, and then we'll get the factorial loadings, etas, through ridge regression. So we have the evidence, and we can lower bound it just through a standard procedure and get the evidence lower bound, and we're going to maximize the evidence lower bound. So we know that the lower bound is tight when the Q distribution is actually the posterior distribution, and we know the form of the posterior distribution, so why don't we just plug it in? The problem is that we can't evaluate this thing. It's intractable because of the posterior distribution and because of the sum over z's. So what we do just Monte Carlo approximation. So on the E step, we will just sample some particles from the determinable point process from the prior. Then we reweight them according to the posterior. So we do importance sampling, and we can approximate this sum. And on the M step, we can do a partial M step. We can do just a gradient step towards the optimality. So eventually, iterating between these two steps will eventually converge to some maximum a posteriori over lambda. Now, we need to do ridge regression once we know the x's and lambdas, and this is just a standard problem. So we solve it in one step. Now, YJ will talk about the experiments.
Okay, I think we're running out of time, so I'll very briefly go over the experiments, as much as we're theoretically motivated by this nice new technology called determinable point processes. This problem is basically a kind of an unsupervised learning problem. So one natural metric would be reconstruction error. And these are the plots that we show. And this is from synthetic data generated from a Gaussian mixture model. I want to emphasize that you could get similar results on the data that's generated from our model itself. But I just wanted to show something that's not necessarily generated from our model, but it still kind of works. So the x-axis is the number of iterations over the entire data set. And I want you to look at the bottom two plots for now. The third plot on the left shows that we kind of get, after some number of iterations, we converge to a stable point where we fit each data point with using around 15 to 16 factors, which you can think of as basis vectors or dictionary entries, whichever terminology you're more comfortable with. And the total number of components that we used here is 100. So it's consistently choosing a pretty sparse representation of the data, which is pretty nice. And this plot on the right still shows that we're still using up all 100 factors across all data points. So we're touching